Welcome to The Explainer. Today, we're diving into a network design that's as elegant as it is fragile, the ring topology. It's a perfect circle, a simple concept, but it has one single point of failure that can bring the whole thing crashing down. So, let's get into it. Okay, so let's start with a really basic problem. You've got a bunch of computers in a room and they all need to talk to each other. How do you hook them all up so that messages get sent in an orderly way instead of just a chaotic digital mess? This is the fundamental challenge that network design tries to solve, because in the early days of networking, preventing a data free-for-all was a huge deal. The solution to that problem is what we call a network topology. The easiest way to think about it is like a blueprint for the network. It's the map that shows exactly how everything is connected and dictates how data gets from point A to point B. So how do you create that perfectly orderly network? Well, one of the earliest and honestly most elegant answers is the ring topology. The idea here is just beautifully simple. Each computer, or what we call a node, is connected to exactly two others, its neighbor on the left and its neighbor on the right. The source material describes this as each device having a dedicated point-to-point connection, and together they form this perfect, unbroken circle. And this really shows you that clean, logical layout. You see, there's no central hub or some single main cable that everything plugs into. It's just a continuous loop connecting every single device in the chain. Okay, so we've got our circle, but how does a message from my computer get all the way over to another one if they're not directly connected? Let's break down how that actually works. So, in a ring topology, data always travels in one direction. A message gets sent from one machine to its neighbor, and that neighbor passes it to its neighbor, and so on and so on. But the real magic is right there in step 3. Every device has a built-in repeater. So when a machine gets a signal that isn't for it, it doesn't just pass it along. It actually regenerates the bits, making the signal brand new and strong again before sending it on its way. And this is absolutely crucial. That repeater function means the signal quality doesn't get weaker as it travels. It doesn't matter how many computers are in the ring, the very last computer in the chain is going to get a signal that's just as strong as the very first one did. But for all its simple elegance, this orderly design has a massive vulnerability. It's a true Achilles heel, one that can bring the entire system to a grinding halt. Now, in a perfect world, this is what you get. Our source material points out that in a healthy ring, a signal is circulating at all times. It's this efficient, continuous flow of data just moving predictably from one device to the next. It's beautiful. But what happens when things aren't so perfect? Well, the source text couldn't be any clearer about this. It says, and I quote, "A break in the ring, such as a disabled station, can disable the entire network." And right here, you can see the problem in action. If a single cable gets cut or maybe one computer just goes offline, the circle is broken, the path is gone, and just like that, the entire network is down. All communication just stops. The main thing to take away from this is just how dramatic and all or nothing this design is. It either works perfectly or it doesn't work at all. There is absolutely no in between. So let's get to the final verdict and see how this all balances out, because we've got some very clear pros, one massive con, and thankfully, some very clever solutions. So on the plus side, our source notes that a ring is pretty easy to install. If you want to add a new device, you only have to change 2 connections. And finding a problem is simplified too. If a device stops getting a signal, it knows the problem has to be with its immediate neighbor and can sound an alarm. But on the downside, that one-way traffic can create delays. And of course, there's the big one. A single break brings the whole network down. So how do you fix a fatal flaw like that? Well, engineers came up with some clever workarounds. The source points to 2 main solutions. You could use a dual ring, which basically creates a redundant backup path for the data, or you could use a smart switch that's able to detect a break and automatically reroute traffic to bypass that failed section of the ring. And that really brings us to our final question. If this basic design is so incredibly fragile, why is it so important in the history of networking? I mean, how did a concept like this even survive and evolve? Well, the answer is that the simple ring was a critical stepping stone. The core idea, passing information in this controlled, turn-based circle, that became the basis for a method called token passing. You can think of it like a talking stick for networks. This concept was the engine behind much more robust and influential network types like token ring and FTDI. So the simple ring, for all its flaws, really did lay the groundwork for the more resilient technologies that shape the networks we all use today.